Welcome back to the lectures on high performance scientific computing. So far we have been discussing on how to program shared memory parallel computers. We have been looking at this through the programming of the OpenMP paradigm. Today we will start looking at message passing basics and also essentially looking at how to program distributed memory machines. For that, we need to revisit what distributed memory machines are. We'll just have a brief discussion of it and we'll see what are the challenges in programming such machines. So if you recall, in distributed memory machines, each node has a computer which has only a locally addressable memory space. Several of these machines are then connected via some high-speed network. It could be something as simple as a Wi-Fi router, or it could be something very specific to a high-end communications device. The idea here is that you are essentially taking several computers of similar specifications and connecting them via an interconnect where they cooperatively are able to do some large calculation. But because these are distinct machines, the fact of the matter is that each CPU is now connected only to its local memory and its local disk as shown in the diagram. So effectively what happens is that when a program is being executed, it has access only to its local memory. If it needs any data which doesn't reside in its local memory, it has to be communicated via the network interconnection. Now, this poses a challenge on how to program these machines. But the advantage of this machine is that you could build as big a machine as you would like. In shared memory machines, we had discovered that there is an upper limit to the number of processing cores that one can have. And that is usually determined by the silicon wafer technology that is being used or the microprocessor technology. Here, the only thing that limits us is physical conditions such as the amount of room we have, what is the power and cooling capacity we have, and most importantly, how much money we have. These are cheaper to build because you can take commodity machines and attach them via the interconnect, and you can scale them as much as you want. Now, the immediate disadvantage is that obviously these are harder to program, as I said, because we need to communicate any information that is not locally available. And when we split up a large program, usually large bits of the data are not available. So now let us see how do we effectively program these machines. One of the effective standards for programming such distributed memory machines is called as the message passing interface or the MPI library. It essentially does communication between several processes which are running on different computers. Unlike OpenMP, which is like a language or rather a directive-based language which required compiler support, MPI is a library. So it essentially means that it provides extra functionality which can be exploited by a regular standard serial compiler. It supports several standard programming languages like Fortran 90, UPC, C, so on and so forth. The message passing itself is some sort of a paradigm. All it really does is that it exchanges information between these distributed computers. And it's really easy, or rather I shouldn't say easy, it's rather very flexible to implement these paradigms. How the network is shaped also has an effect on how these communications take place. But to the MPI programmer, it does not matter whether you're connected in some sort of a fancy interconnect or something very simple as a simple Wi-Fi. You can keep extending this to as large a machine as you want. You can also use the same MPI process to run multiple processes on a single workstation with multiple cores as well. Now, the advantage of this is that you could write and test small programs on a local machine which has multiple cores, and then finally when the program is ready to be executed on larger machines with larger data sets, you can easily port it to these large distributed memory machines. So, in order to do basic MPI programming, you need some basic functionality. You need to have the ability to start processes or programs. You need to have capability to send messages, receive messages, and obviously synchronize these messages. Remember, we are running these codes distinctly on different distributed machines. So, in effect, they are actually separate but identical codes working on slightly different data sets. And this has to have the capability to send and receive messages. Only then we will have some element of parallelization. If you just had the capability to send, to receive and synchronize, you should be able to construct any sort of parallel program with this functionality. Over this next few lectures, we will look at these basic versions of MPI routines which allow you to implement this. But MPI also offers several other functions which make things more convenient. But with those 4 basic capabilities, you should be able to construct any algorithm. And most of the MPI codes will be using just these routines. So let's now look at a simple example of a hello world program. First, we need to know how to execute this program. I will show you the implementation of the simple hello world code very soon, but let us first look at how to execute it. So when you execute it, you have to issue a command something like MPI run -np8 a.out. So let us first decipher this statement. A.out is the executable file, as we know, which basically is going to run the code. When I invoke MPI run -np8, what it is effectively telling me is that I need to run 8 instances of this program across 8 different machines or 8 different cores, as the case may be. In this case, since we are running it on a single workstation, it is on the same machine but across several cores. And what the code is doing is that it is just outputting hello from each of these processes. Now, let us look at this code and see if it is very complicated. The first thing that we need to have is to include the MPI header file. This is because, as I had said, MPI is a library and you need to have the appropriate function declarations and function calls. The definitions of these functions reside in this header file. So, if you look at it, once the program starts, we have an integer which basically says my process number, PENUM. Then we have an initialization function. So, what this initialization function does is that it takes in 2 arguments from the command line, which essentially tells it how many MPI processes need to run. Also, if there are any additional information bits like where do we need to run these processes, you can specify them explicitly, or you could use some advanced sophisticated queuing systems, which we will discuss later. So, the first bit of information that comes to this code is that you need to run multiple copies of this code. So, the MPI init function takes in the information of how many copies of this code need to be run and where do they need to be run. By default, if you do not give anything, it will be run in the shared memory mode, or I should not say the shared memory mode, because each of these machines, while the memory is in the same physical memory, they are not accessible by the individual copies of the program directly. So, MPI init essentially takes care of initializing the multiple copies of the code. Then next function, MPI communication rank, tells the information of what is the process ID. Now, since we are starting several copies of the same code, one needs to distinctly identify each of these distributed processes. Each of these distributed processes are given a separate ID ranging from 0 to the number of processors minus 1. So the function MPI communication rank or MPI com rank takes that information of which unique ID has been assigned to that particular process, and it puts that number into the variable myPenum. If you notice here, because this code is being run as several n distinct copies, each of those n distinct copies have their own local copy of myPenum. You do not need to explicitly say that myPenum is a private copy, as we had done in OpenMP. So by default, all variables in MPI are private to that particular process. Here, then we go on to say printf hello from so and so process ID. And finally, we have the last command, which is MPI finalize, which essentially closes all the programs that have been started amongst different processors and cleanly exits. A comparative Fortran version looks like this, where again I have to include the function definitions using include MPI f.h. And here I call very similar functions, call MPI init, MPI communication rank, and MPI finalize. All of these functions between Fortran and C are almost exactly similar, except that there might be a couple of variables where the input variables might be slightly different. For example, in Fortran, here you have to specify what error code is to be returned. Whereas if you go back to the C code, by default, MPI init does return some integer value if you would like. So let's now go and see how does this code behave and how does it run. I will now open up this MPI Hello World code. So here you see this is the simple implementation of the MPI Hello World, which is the exact copy of the code which we saw in the slide. The first thing that we need to do is compile this code. To compile this code, we cannot use the traditional GCC compiler. We need to use something called as MPI CC. This is because the code now has MPI functions which need to be recognized, and the MPI CC command basically wraps around the library along the base C compiler, which then recognizes the functions as MPI functions and provides it capability to start these different processes, do the communication, and synchronize, so on and so forth. So now let's compile this program hello world.c and put it into the output hello. So now we have an executable named hello. Now this code is compiled and is ready for execution. To execute this code, now I will have to call another command. We cannot just simply run the code hello. If we do that, it's going to run in essentially what is a serial mode, because there's only one process which is going to start, and we will just have hello from 0, which is the first MPI process. If I want to run multiple processes, I need to use another command called MPI run, and then I need to specify how many MPI processes we need to start. So this being a shared memory machine, I am now going to run it with, let's say, 4 processors. So I say MPI run -4, P4, and then the executable followed by hello. So when I run this, you will see I will now get responses from 4 different processes. I can change the number of processes to something higher, and now I will get a response from 8 different processes. One thing that you will notice is that every time I execute this code, let's say with 8 processes again, the order in which the responses come is going to be different. This is because when you do MPI run and execute this code, there is no particular process which has any special preference. What do I mean by that? That means that processes 0 through 7 all are treated equally, and it is any process which finishes first is going to put the screen output. And that is why we have need for synchronization when we do some calculations. How many MPI processes can I start on a single machine? Let us say that this particular machine has 24 CPU cores. Can I start 24? Can I start 12? Can I start 48? The answer is I can start as many as I want. Then what happens is that all those n different processors are treated as n distinct programs by the operating system, and they are scheduled on the CPU according to the OS's scheduling policy. So let us assume that we had 48 MPI processors running on a machine which has 24 cores. So the OS at that point will take a decision to schedule 24 processors at a time and take in and out the processors as it deems fit. Now, which processors get scheduled? We have no control over that unless we execute some specific commands. So now let us try to see what happens when we execute, say, 48 processors. And you'll see that you have now 48 different hellos coming out from here. Okay, now let's go back to the slides. So let's make a few general observations at this point of time. For a general MPI code, you will always need to include the header file mpi.h in C or mpif.h in Fortran. MPI calls are always sort of easy to identify because they always start with MPI underscore, and the calls themselves are usually the same in most programming languages. As I said earlier, for Fortran routines, you have an added argument which gives out the error code or the error condition if there's a problem in executing these functions. Whereas in C, the function itself returns a functional value which is to be interpreted as the error code. These error codes are very useful to debug the program if something goes wrong. But most probably you will not find a reason to use them. Now let us discuss the functions a little bit in depth. So the first function in any MPI program before we start parallelization always has to be MPI init, which essentially initializes the MPI environment. So this thing does a lot more work in the background. So what it does is that it first creates the distinct copies of the program. Remember that you are passing an argument at runtime on how many copies of the program need to be executed. And in certain distributed memory machines, you will have to execute this program on a different physical machine itself. So that means this MPI init program has to communicate to this other machine which is connected on the same interconnect, and then has to start the program there and take in all the required information. So essentially, this also needs to point the code to the correct executable on a different machine. So we need to have some sort of network file system which is common across all these distributed machines so that they all have access to the same code. So once MPI init gets started, it starts up all these programs through different means on different machines or the same machine depending on how you have configured it. The other bit of information is if you have to start the program on different machines, you have to specify what those machines are, typically their network addresses, and how many processes on each machine you need to execute. Through a later example, we will see how to do this specifically. We need to specify something called as a machine file, which picks up all the information about where these machines are located and how many processes each machine have made available. When you look at advanced machines where there are many users, typically this is done automatically through a queuing policy. Essentially what you would do is that you would submit your code to a queue, waiting for it to be executed when there are resources available. Once the resource becomes available, the queuing system then provides this information to the MPI program about where this code can be executed with how many resources. The last function that is executed in an MPI code is always MPI finalize. This is sort of a companion to MPI init. If MPI init is the first bit of MPI code that will be executed, MPI finalize will always be the last bit of code which is executed. And it must be a last MPI call always. What it does is that it cleanly shuts down all the programs which are being executed. It releases all the resources that are being consumed. So there are a lot of housekeeping things that a code does, like taking care of variables, storing data, so on and so forth. If you do not execute an MPI call, it's quite possible there will be many hanging programs which will continue to linger and which will jeopardize certain resources. So it's always good to be a good citizen and issue an MPI finalize. If you did not do it, typically your code will not know or care about it, and it will just keep continuing to execute. Think about MPI finalize as some sort of a termination signal which is being sent to all these codes. Now, as we said, MPI communication rank function is where the distinction lies. MPI init and MPI finalize are absolutely the same code which is being run on all these processes. But MPI communication rank is the one which gives a distinct identity to each bit of code. Because if you do not have a distinct identity, then it will be difficult to do any meaningful parallel calculation. So what MPI com rank does is basically get the assigned process ID, which is a unique address for each MPI process that is being started. The communication rank is the one which actually obtains this number. The number is assigned when you do the initialization. And the unique addresses start from the number 0 and go on to number of processes -1. And that's the only thing that sets each of these codes apart from other. And you can use this process ID as the key discriminator which will then allow you to construct your parallel algorithms. Because ideally, you want your parallel algorithms to work on different parts of data and not on the same data. And using this PEID, your code will take different input data, will do different branches of code. So when I run hello world, essentially what happens? In this case, I am depicting that we have 8 copies of hello world, which essentially means that I have MPI run minus NP 8. So 8 distinct copies of this code are created. They are passed to the 8 different processing cores, and each one of them is executing that bit of code and then returning the value. As I said, the order in which they come out doesn't matter. Each of them have their own priorities. There is no special identification for a master or a slave process. That is now left to the programmer on how to handle it using the discriminator of process ID. So once we execute this code, we cannot expect that the code will come out in the same order every single time. The other question that you might ask is, how does the output know where to go? So we do not know where the source is, in the sense that if we are now running this code across a set of distributed machines, where is a terminal where this output should go? This automatically is decided by the MPI environment. Remember, when we execute it with the MPI library, we have now initialized an environment, and the environment then assigns this MPI code to different machines. It knows where is the final terminal where the output needs to go. Obviously, the most important thing is how do we manage disk writes for output of scientific calculations. And we will look at that in future classes. Thank you.